Today we're going to be getting into a heavy subject. We're going to be talking about mass and how to compute it. Sometimes it's easy, but of course sometimes things can vary. And how do we handle it? Well, spoiler alert, break things into easy to handle parts and put it all back together. And the other thing we'll talk about is how to find our center. So it's going to be a great day today. Let's begin. So suppose, let's start in the setting where we have a one-dimensional shape. We're going to think about it as a very thin rod. So I have this thin rod going from A to B. Now, associated with this rod is a density. And let's just suppose constant density. So, in other words, that was mass per length. Well, then if I want to compute the mass, I multiply the density times the length. And we're done. Okay, we'll often use the symbol delta for density. They both begin with D. Well, what if it doesn't have constant density? In other words, maybe it's the case that it's a little bit thicker at one end than the other end, or maybe there's a different material from one part versus the other part. And so as a consequence, it's not uniform. Well, how do we handle it? Well, we do what we always do. If we say, well, look, if something is varying, let's break it into small parts. So what we'll do is we'll come to our rod and we'll start chopping off little tiny pieces. So now all of a sudden, we don't have one rod, we have lots and lots of little tiny rods. Now, what's the advantage of breaking things into little tiny parts like this? Well, the advantage of breaking things into little tiny parts is if we pick a part, say, here's our part here, then we say, on that part, the density varies so little that essentially the density is constant. So we say, aha, now we can get a good estimate. So we can treat the density on a small part as constant. That's the whole idea. Now, that's also the philosophy, of course, when we talked before about things being flat. Really, when we talk about things being flat, it means things are easy to compute, or in our case, they're essentially a constant value. So we're now ready to figure it out. We say, look, if I want the total mass, I just say, what's the masses of the little pieces? If I want the masses of the little pieces, I say, all right, it's going to be approximately the density somewhere in that piece, because that piece is so small, it doesn't matter where you look, the density is essentially the same, up to very tiny error. So that's why you see this approximation. Well, because the density, there's a little bit of error. But anyways, the density of the piece times the length of that piece, that's the mass of the piece. So this part right here, this is the mass of one part. Well, then what do? You say, hey, I have the mass of one part, add them up. That's what our sum means. And now, of course, we say better and better approximations if we make things smaller and smaller and smaller. So as we increase the number of ways we chop things up, our sum becomes an integral, start to finish. Our density becomes a density, and our delta xi becomes a length. So this is really saying, hey, density times length. Mass of a little piece, add the pieces up. Now we know how to read the formula. Once we know how to read the formula, we know how to understand it, and also importantly, how to adapt it. It's good to be adaptable. So that's mass. That's not so bad. Just break things into part, add them up, and you're done. What about the center of mass? What is that? Well, you can think of it in a couple of different ways. You can think of it as a balancing point. So if I had a rod, let me choose a little bit darker color here. So here's a rod. If I was looking for the center of mass, I would look for the point where it would balance just right. So in other words, if I put a little point underneath, it wouldn't fall one way or the other. It would stay upright. Now, how do we find it? If we have constant density, it's in the center. Now, if we don't have constant density, it's going to move. Well, how? Well, you can imagine I have a very thick end and a very thin end. And so where is my center of mass? Well, it's going to be biasing towards where the mass is. So essentially the center of mass should be influenced by what the location of the mass is. And wherever it has more mass, it should be moving towards that location. Now, not completely, because there are other places where there's mass. It has to be balanced out. Now, the way I like to think about how we find the center of mass is it's a weighted average. And so what's happening is that we're having all these different places where the mass is located, and all of them are saying, hey, take me into account, and so forth and so on. And we put it all together, that's how we're going to get the center of mass. And we're going to go into that in just a second here. But before we do, there's an important note here, a word of caution. When we talk about this example, where we say, hey, the density is constant, so that means the center of mass is right in the center. Well, it turns out that in this case, it is the case that 50% of the mass is on either side. But that's not always going to be the case. So if you come over here, you say, okay, is it the case that 50% of the mass is there and 50% of the mass is there? The answer is usually no. No. You see, the center of mass is not the point where you have half the mass on either side. So that's a distinction. It's a different type of thing. We'll do an example during the practice where we actually work through and explicitly find the center of mass and explicitly find the cutoff point, and we will see that they are very different. And at least, well, the process is different. So let's get to this weighted average, and how do we think about it? So here's how we think about it. So I'll start with a very simple example. Imagine we have a class, and in the class we have, say, quizzes. The students are taking quizzes. There's 10 students. It's a very small class. And the scores range from 0 up to 5. And now we say, okay, people take the quiz, and 2 students got a 0, 5 got a 4, and 3 got a 5. And I say, now, what's the average score? How would you find it? Well, what you do is you'd add up the scores. You'd add 0 and 0, and then you add 4 and 4 and 4, 5 times, and 5 and 5 and 5. And then you divide by how many students took a quiz. So if you do the computation, it's not very hard. What do you end up with? Well, okay, it's 2 times 0 plus 5 times 4 plus 3 times 5 over 2 plus 5 plus 3. And it turns out to be 3.5, which is right there. Now, what's happening? Well, we can think of the scores as being a mass. And so in some sense, we have like, how is the mass distributed among these points? And what we're doing is we're saying, all right, where's the average location of the mass? And the way we do that is we ask ourselves, okay, let's have every single piece of mass, it gets a vote, and we add up where the votes are and take the average of them. So when I'm multiplying here, it's the value of the mass times the location plus, see, that's 2 times 5, and the mass times location, 5 times 4, mass times location. So then I divide by 2 plus 5 plus 3. So it's the weighted average of where the mass is located. That's how I like to think of it. And if I remember it that way, it's pretty quick to rederive the formulas. So how do we actually do it? Well, it's a very similar process as before. So what we're going to have is the following. We're going to say that the center of mass is, we're going to add up on the top, such as we have here, the sum of location times the mass at that location. So that is sort of saying, okay, this is how much of a vote you get, and here's what you're voting for. Divide by the sum of all the masses. And in the end, we're essentially giving an average weighting for the x's. Places where there's more mass gets to have more of a say. Places where there's less mass gets less of a say. So its bias is towards the larger masses, but it doesn't completely ignore the smaller masses. Now, a couple of things here. This top expression is called a moment. And so when you think of moment, usually you will think of it as a mass times a distance. And This is actually, to be more precise, it's called the first moment. And the reason it's called the first moment is its distance to the power 1. You can talk about things like second moments, and that gets into a subject called inertia. That's not what we're going to talk about for today. So that's the one thing. You might also say, all right, I notice you have some notation over here. The m per mass, okay, I get that, m per mass. M per moment, well, now things get confusing. And then you have this 0. This is a 0. What is that referring to? So here's the thing. Whenever we talk about a moment, what does a moment have? I say it's mass times distance. Really, distance is a little bit misleading. A better term is location. But oftentimes people prefer distance. So when we talk about a distance, we always have to say a distance relative to what? So the subscript is giving our answer. So here in the one-dimensional setting, that's where we are right now, we say, well, we're going to take our distance relative to 0. Now, here's why it's better to say location. Because when we talk about distance, distance should always be a positive measurement. We want to treat negative x values as negative and positive x values as positive. So we want to keep track of the sign. So just keep that in mind. We do want to have this be negative or positive. So we're not going to have any absolute values floating around in that part. All right, well, that's great. Now we do what we always do before. We break things into pieces and say what happens. Well, here in the pieces we can see it's the location, x, times the mass. We know how to do mass. Mass is density times length. So x is location, delta x times dx, mass, multiply them together. That's the moment of one little part. Add all the parts, and now we have our moment. Divide by the mass. And a similar process, which we've already talked about before. It's the density times the length of one little part. So this is the mass of one little part, and we add them all together, and we're done. So the weighted average of our locations, where we weight based off of the density, essentially, at those locations. All right, now that's one-dimensional. Okay, one-dimensional, great, we can do that. How about two-dimensional? Well, we have to think about what's going on. So, here we go. If we have a region R and a density function which depends only on x, and what does that mean? Well, it's a two-dimensional region, but when I look at the density, I only care about the x-coordinate. It doesn't depend on the y-coordinate. Now, it could be the case that we could turn it and say, well, maybe it only depends on y, in which case we just, all right, change all of our integrals, put everything in terms of y. But the important thing is it only depends on one of our variables. We'll get to why that needs to be the case in just a second. Can we find the mass and the center of mass in this setting? The answer is yes. How do we do it? Well, the way we do it is we break things up into small parts. And then we start saying, okay, well, let's think about what's happening on each part. And if we understand that, we're good. So, how do we understand it? Well, there's our shape, and we broke things into parts. So, we look, say, well, let's look at a part. Let's say this part right here. What we want to be true, and this is sort of the key thing whenever we talk about integration, is that when we break things into parts, the behavior on each part should be flat, or another word is essentially it should be constant. It's not going to change much. And here's why it's important that our density only depends on x. Because if you notice our piece here, it's very, very small change in x. So a small change in x, that tells us that, oh, our density behaves almost like a constant. And when I say almost a constant, it doesn't change much. Density doesn't change very much over that length. Now that's why we want it to be only a function of x. If we were to slice horizontally, only a function of y. What happens if our density changes with both x and y? The answer is we'd have to slice not horizontally, not vertically, but then we'd have to say, well, got to break into little tiny pieces, and then you have two things going on. We're breaking in multiple ways. That's a good task for multivariable calculus, which we'll get to if you stick around. Multivariable calculus, great subject. But for us, we're just going to say only one direction matters. Okay, so that's why we need to have our density depend on one variable. All right, now we're pretty much great to go. It's the same ideas. You see, if we understand where the formulas come from, adapting to a new situation is pretty quick. We say, okay, let's think about our mass. Well, mass would be our density times area now. We're two-dimensional. So, what's our area? Well, it's the height. So the height is from the top f to the bottom g. So f minus g is the height. This delta x is the width. If we take height minus width, we get area. Multiply area by density, you get mass. And when we say mass of one part. So it's the mass of a little piece. And now you add them all together. So it's adding up the densities of the little parts. And we can now see where everything in the formula comes from. So we say, okay, perfect. So for our mass, you're adding up, which means integrating, our density times our height times our width. So oftentimes, when I'm thinking of the formula, I don't memorize it in this format. Oh, delta x times f of x minus g of x dx. I think of it as, okay, it's density times height times width. And away I go. And life is good. All right, great. Well, now what? Well, now we say that's the mass. What about the center of mass? So we have to talk about two coordinates, the x-coordinate and the y-coordinate. Well, okay, so here we go. Remember, we have that moments involve distance, and a better word for distance is a location. Now, location to what? Well, we're going to talk about two locations in particular. It doesn't have to be those two. It can be any location, really. We're going to talk about the x-axis and the y-axis. So, what's the distance from the y-axis? Well, so let's, again, we pick a little piece. So we pick a little piece. Doesn't really matter which piece we pick. Let's say we pick this part right here. So there's our little piece. And here's the key. This is one of the nice things. It says, look, if I have a shape, I can think of that as really just having all of the mass located at the center. That's one of the nice things about having a center of mass. It says, hey, I have this big object, but I can treat my big object as a single point wherever the center of mass is with that heavy mass. As an example, you can model something like the solar system. You don't have to keep track of every single object on the Earth and say, like, well, there's a paperclip here, there's a banana over there. It's like, well, no, the mass of the Earth is one number, and I'll treat it as though that the Earth were a single point with a lot of mass. Do it for all the planets, and then you can get a really great idea for how everything interacts with each other. Similar idea here. We say, okay, look, we're going to treat it as though there were just one point, and all the mass were at that one point, and that point is the center. Well, if you have a rectangle, where's your center? The center of your rectangle, well, you just find that the center in terms of x and the center in terms of y. So there's the center of mass. So that's how we say, okay, that's where we're going to talk about our distance from things. So where are we at? Well, we're going to do the distance from the y-axis. So that's m sub y. Now, this is the part that initially when you hear it, it just feels so wrong. But once you get the hang of what things represent and how they connect, it becomes pretty reasonable. So m sub y is the distance to the y-axis. So we say, well, that's this distance here. This is our distance to the y-axis, or our location for the y-axis. And we say, hey, if I want to know how far I am from the y-axis, that is x. So x told me how I moved off the y-axis. So now we say, all right, we have our pieces. Our location, then we have our density, and then we have our height, and then we have our width. So those are our 4 pieces. And if you think, height times width is area, area times density is mass. Mass times location is moment. Add the moments up, we get the total moment. And now we're done. Now, of course, you can memorize the formula, but then it's a little bit harder to adapt. I mean, what happens when we switch? Maybe our density is a function of x, maybe it's a function of y, and then you're like, ah! But if you remember, oh, I have my pieces here, what all my pieces represent, you're like, oh, and life is good. Okay, so what do we do? Well, we say, what does it become in the limit? If we're adding up, that becomes an integral. Our x location, our density, which depends on x, our f of x minus g of x, our height, and our dx is our width. So, okay, that's the moment with respect to y. And the reason I say that it can be confusing if you don't understand what things are is you say, hey, when I have an m sub y here, there was an x that you put in there. So now let's talk about m sub x. This one is a little bit stranger. What do you have? Well, here's the idea. If you go back to our picture, we'll keep the same picture here. We have our little piece. We'll mark a piece here. Here's our little piece. And we say, look, we do the same thing as before. We have our center of mass. How far is it away from the x-axis? Well, if I want to get to the x-axis, what do? I drop straight down. So my distance to the x-axis is y. So y is my distance to the x-axis. Now, here's where we have to start thinking about, okay, so when I'm thinking about my location, it's the y value. Well, what is y in terms of x? Because as I'm setting the problem up here where I'm slicing in these vertical slices, I'm going to be integrating with respect to x. Well, the y-coordinate is the halfway point between the top and bottom. So the way you find the halfway point is you take half of the sum, f plus g divided by 2. Now we're ready to go. We say, look, our moment with respect to x is the sum with the y value, the density, times the height times the width, right? And then all our pieces make sense. We're good to go. So we just break it apart as we did before. We have our location, we have our density, we have our height, and we have our width. And once you see it, you're like, yeah, everything fits together, everything's great. And getting back to, I said, look, it can be confusing, is remembering, hey, I'm talking about the moment with respect to x, and lo and behold, there's this y showing up. And that's because when I talk about the distance or relative location to the x-axis, it's y that does it. So that's why the subscript kind of like is sort of the opposite. So if you're looking for m sub x, it's really about y. If you're looking for m sub y, it's really about x. So here, if you remember this, you're like, okay, that makes sense. And now the next step, we start getting into it. Well, y is halfway between f and g. All right, so great. That's easy to understand. And then you say, well, hey, there's this f plus g, there's this f minus g. A plus b, a minus b becomes a squared minus b squared. So you get a half times your density times f squared minus g squared. And then there's a little delta x on the end. And now, of course, take the limit and you say, okay, lo and behold, it becomes the integral of a half times density times this function squared minus that function squared. And if you look at that and you say, what? Where did that come from? That doesn't, it doesn't feel at all like what we did before. Well, that's because the formula sort of obfuscates what happened. What really happened was that you had this distance was a half of f plus g. So you could memorize it in this format, but I think that's a little bit less adaptable. I recommend just remembering, look, if I'm looking for a moment, there is a location, a density, a height, and a width. And figure out what the 4 pieces are and go from there. So that's what I like to do. So we can find our moments, we can find our mass, and we say, well, to find our center, we just divide. So if we take m sub y divided by m, that's the average of the x-coordinate. Now, why is it m sub y? Well, go back to what we did for m sub y, which is back here. See, m sub y, you're voting based on your x. So when we do m sub y, it's the average of your x values, weighted according to mass. And when you do m sub x, your location is based on y. So it's you're averaging your y values based on mass. So that's why there's a little slight twist there. But now you can find your coordinates easy. Life is good. Life is good. All right, well, some notes. We've already talked about pay attention. M sub y helps find the x-coordinate. M sub x finds the y-coordinate. Another nice thing is think about symmetry. So you look for symmetry of an object. What does that mean? And this is actually a little bit more subtle than it sounds. So what it means is, suppose I have a shape, and let's put it as a circle, something very symmetrical, and I say, all right, where's the center? Now, if I don't say anything about the mass, you say, well, that's easy. The center of the circle is the center of the circle. Okay. Now, if I don't say anything about density, assume constant density. Now, what if it's not constant density? What happens? Well, the answer is it depends what the density behaves like. So, what can happen? Well, what can happen is you could have something where on one side it's very not dense, but then as you got over to the other side, it became very dense. So what's happening here? Well, what's happening is that somehow it's a little bit more denser towards the right. Is our center of mass still in the center of the circle? And the answer is no. There's now this bias pulling it to one side. So the center of mass is going to move. So it's not just enough that your shape is symmetrical. What needs to be true? Well, you have to have your shape and you have to have your density. You have to have both. So is there any symmetry left? Well, the answer is yes. If I look here, and what would happen is when we flip across that line, so it's like we take it and go boom, if the shape stays the same and the density stays the same, that's a line of symmetry. Anywhere where you have a line of symmetry, the center of mass has to be on that line of symmetry, which is great. It's a wonderful tool because what it tells us is, hey, if I know a line of symmetry, I can sort of cut my work down. So I can say all I have to do is find where it is on this line. For instance, here, this could say, look, I know what's happening with the y value because the center of mass has that symmetry. Therefore, I don't need to worry about the x value. So we cut our work down somewhat by half. Well, technically speaking, by a third, because if you're looking for a center of mass in 2 dimensions, there's 3 integrals. There's the mass, the moment with respect to x-axis, the moment with respect to y-axis. And so if you take off one dimension, you only have to do one of the 2 moments. But still, that saves us work. So that's good to know. Now, another thing that should be noted here is that centers of mass have to be somewhat central. Now, it doesn't mean it's in the middle of the shape, but you might have the following. You say, look, here is my shape. I have my blob. It does whatever it is. Its mass is something. I don't know. It can be uniform or not uniform. But what should be true? Well, if I run the computation and I say, aha, my center of mass is over here, what can we say? Well, we can definitively say it's wrong. Because there's no way. Because look, the center of mass should have somehow central to the mass. And look, if all the mass is on one side and the center of mass is over there, forget it, hopeless. It means a mistake was made. So once you get an answer, you should say, okay, where is that answer? And does it make sense? Is it within the shape? And even if it's within the shape, is it where the mass seems to be at? In other words, am I leaning towards where there's more mass? If one of those things is not happening, it's outside the shape, or it's somehow heading towards where there's not very much mass, let's check our setup. There's potential that errors have been made, and we'd like to prevent that from happening. So that's just something to keep in mind. This falls into the, is my answer reasonable? You know, we want our answers to be reasonable. If they're not, well, that's unreasonable, and we should fix it. Okay, so those are some notes on the center of mass. It is possible, by the way, that your center of mass does not lie in your shape. You can easily construct shapes where this is true. A very simple shape that does it is if you take just a circle and punch out a circle, but you make it constant density. Well, where's your center of mass? Well, the answer is it's right in the middle of the hole. So look, your center of mass doesn't have to be in your shape. I'm not saying that, but it has to be a reasonable answer. That's what I'm saying. Okay, one last idea. We're not going to go into this much because at this point, we should be able to just say, yeah, this is just adapting the idea in a slightly different setting. And the new setting is saying, well, what if you have wires? Well, what is that? See, we've talked about one-dimensional setting where we had a rod. And a rod was something like this. Here's our rod. And we talked about what to do. Well, the density times length, right? So our mass was the integral delta x dx, a to b. Well, what if we didn't have a straight rod, but it was somehow curved? So that's what we mean by a wire. We've taken our rod and moved it so it does something. Now, it doesn't have to have uniform density. You can imagine that if it's a wire, maybe it starts off very thin, and it gets very thick, and very thin again. Maybe it gets thick also towards the end. And now we can talk about, well, what's the mass? What's the center of mass? These are all reasonable questions to ask. So we just have to think about, well, what are the analogous pieces? And if we think about what we had before, we said, well, look, we had a density times a length. That was what was happening before, density and length. Well, now we say, hey, let's do the same thing here. We can chop it up into little tiny parts. And now we have a density. So that's our delta x. What's length? Well, we've talked about length on curves. That's one of the things we learned how to handle. And that is this part right here, the square root of 1 plus f prime of x squared. So we're thinking about this as a very special type of curve, namely the curve y equals f of x. And so this becomes the length. So you integrate density times length. And there you go. And now you found the mass. How about for your m sub y? Well, you just need to say what? What is m sub y? M sub y is the moment, and you're looking with respect to the y-axis, so you have a location. The location relative to the y-axis is x. So we say, okay, you have a location, and then you have density times length, so location times mass. And here, moment with respect to x, well, the moment has a location built in, right? So location, since it's here, this x, these subscripts are telling us with respect to what? Y-axis or x-axis. Distance or location to the x-axis is y. So here, when we talk about this f of x, it's really just saying, here is my value for y. written as a function of x. So everything has to be in terms of x. So location, density, length. And we add it up. So there we go. And really, once you understand the pieces that go into a formula, it's very easy to adapt to new situations. That's why focus on what do things represent. Don't memorize 100 formulas because that requires a lot of work. Memorize a half dozen ways to set up an integral, and then you're ready to adapt to all sorts of new situations, and you're more likely to get it right when you set it up. So, of course, the other way you're more likely to get it right when you set it up. Practice, practice. So keep doing that practice and keep putting in the work. You'll get there. All right. Well, sounds like a good suggestion. Time to head out and go do some practice.